So, good morning, everybody. Welcome to day number 5. I see some of you have been exhausted, and not all have shown up yet. However, the last day is devoted to some more information about high-speed imaging towards 4D imaging, as well as to some application examples where we again see some of the techniques briefly repeated and then applied as well with the intention to show how you can extract from this information really a better physical insight. I would like to point towards the last aspect we have discussed yesterday. We have shown about the limitations you have using a high-speed intensifier. So I've shown checks where we have illuminated these intensifier with a homogeneous light source at full frame. And that is something we have done once, and I don't recommend to repeat that, because an intensifier does have a certain lifetime only. And by a full illumination with something like 70 or 80% of the maximum intensity that intensifier can take, you use up the lifetime relatively fast. And so that's why this was once a demonstration where we have for a specific instrument shown where the limitations are. So in a typical experiment, very often you have only very short exposure times. Maybe you take it for 1 second, afterwards you close it again in the time where you store your data, even when the flame is still burning. Protect that intensifier such that and as well the images you're looking at very often are not completely filling the whole field of view, such that the consumption of the lifetime is not as large as in these demonstration experiments. So I just want to make sure that you, by that, not, let's say, use up a significant amount of the operation time of a very expensive piece of equipment. Okay. As I said, we want to now continue with the discussion of high-speed imaging with an intention as well to go for 4D imaging. And that brings us to the motivation in this specific aspect, why volumetric imaging combined with the time information can be useful. Then we will see how you can achieve that, either by scanning devices or by multiple sheets, or going to a tomographic approach, which will be exemplified here for laser-induced fluorescence. And that is a very recent development, this tomographic LIF, where first demonstrations have been published in the last symposium. Okay, so first of all, when you're dealing with turbulent combustion, then you're dealing with a 3-dimensional problem, which is, of course, changing as well in time. And so, from that perspective, it seems to me at least natural that it will be useful to get a better insight into what's going on, to look into a volumetric visualization, which is as well time resolved. And this is here called 4D Diagnostics. Of course, it's only quasi-4D, because very often you do not get it really continuously, but only discretized. That's one thing. And of course, you can discuss that term when you, for example, take species on their own as a dimension. Then already Raman Rayleigh, measuring, for example, these 7 species concentrations and temperature, would have had already in the state space 8 dimensions. Yeah. So, however, here this term is meant volumetrically and time dependent. And now some arguments follow why these efforts might be justified. So when you do 2D imaging, and no one really has questioned that when it came up, the interpretation of the data is not always very clear. I give you an example from a lifted flame, where you see here in these blue and reddish areas the instantaneous location of the OH radicals in a cut. Overlaid to that, you see the velocity vectors obtained from stereo POV, together with the out-of-plane motion, the out-of-plane component Vz in color codings, yeah, between green negative and red positive. And then eventually you find something like that that has been discussed by several authors in the past, where you find islands that are disconnected. And that has been interpreted in different ways. It could be, for example, something like autoignition. In this case, you can exclude that. However, in others, it's maybe not so clear. And so these pockets seem to be disconnected and then eventually actually merge. So the question is that maybe not an isolated flame kernel, but is in the third dimension somehow connected. And to answer such a relatively simple question, a 2D information is not sufficient. Or when you do measurements in an engine, where you do have, of course, a full volumetric flow field, then we restrict ourselves with 2D very often to, let's say, specific planes, central tumble plane, for example. But without seeing what's actually happening in the neighborhood of that plane, you cannot really easily understand what's going on. And that's why as well in fluid mechanics, this is a development that is ongoing and for a longer time already. People came up with these approaches like tomographic PIV that we have briefly discussed, with the limitation you might have that you have only a couple of millimeters you can achieve in the depth of field and the out of plane direction. But there have been as well other developments like holographic PIV, where you as well have a chance to reconstruct the three-dimensional particle position from which you then taken in at least two shots the volumetric velocity, or more recent developments called shake the box, which is actually nothing else than volumetric particle tracking, but in a time-resolved way, where you then follow the particles along their path over multiple time steps. So I think this development clearly started in the fluid mechanics community and has been taken over partly into the combustion diagnostics, has been seen as a very useful thing. And now the intention is to complement these kind of volumetric flow field measurements as well by at least qualitative scalar measurements. To come back to the point where you have then information simultaneously on the flow field and at least something like a flame front, structures of the flame that allows you to come up with conditional statistics, as I explained yesterday, but now in a volumetric way. So in the scalar field, things are a bit different than in velocimetry. In velocimetry, based on particles, it is easier to identify their three-dimensional position. In the scalar field, you do have a continuous distribution of your molecules. And that's why it is not so easy without having this clear contrast to identify where, let's say, in a certain volume element filled partly or with the molecules under investigation, where this actually is located. And so there have been proposed different methods. One method is to use crossed sheets, for example, by using LIF, PLIF, or as well maybe planar Rayleigh scattering, that we have seen yesterday in the experiment in the Sandia National Labs. So you have one sheet, you have another sheet, and they intersect at one line. And then you can, from the information, even it's only qualitative, of course, from OH PLIF or Rayleigh, you can reconstruct the orientation of the flame front at the intersection line. And that has been combined with 1D Raman-Rayleigh, such that then if this is the 1D Raman-Rayleigh line, you know the inclination angle between this 1D information and the flame front. Okay, but this is then restricted to the information along that line if this is, as I said, defined by the intersection of these two sheets. Another possibility is to use multiple parallel sheets to come up with something like a quasi-3D imaging. The more planes you have, the better the resolution might be in the out-of-plane direction. There is one possibility to simply scan pulses. If you have a high-speed laser, let it be a burst laser or a continuous emitting pulse laser, which is then swept over the region of interest, over the volume, back and forth. And so that dates back many, many, many years. And I'm not sure whether Ron Hansen has been the first one, but at least he was among the first doing that. Another possibility is that you simply use a bunch of lasers, as shown over here. And Jürgen Wolfram, 20 years back, as well did some experiments where 3 laser sheets have been used intersecting a turbulent flame, and then OH fluorescence measurements have been combined with planar Rayleigh measurements. Okay, the third method that came up only recently is to perform a volumetric illumination of your area, let's say of to excite molecules like OH or possibly as well CH, and then with multiple projections do tomographic reconstruction. But because in turbulent flames, of course, you have a limited measurement time and, of course, a limited number of so-called projections, meaning observation directions, this field is called limited data tomography. So I will not go into the algorithm of that. You'll find as well commercial solutions for it. Of course, that is a key to really have a good reconstruction. But here, with the remaining time we have, I think we should only look at the limitations such a technique brings. But there is, of course, room for improvement in my understanding. So I would like to start with a simple visualization of a rather as well simple experiment that has been conducted in my lab many, many years back, where we were using Mie scattering. Using Mie scattering means you don't need so much laser power. Yeah, you can use high-speed lasers with only small pulse energies. And based on that bluff body-based swirled burner here, you see a small modification. Again, you have here the annular slot surrounding a bluff body, and the bluff body has been now replaced by a bluff body with a tube from which you had a jet emanating into the surrounding co-flow, emanating from that annular gap, and only these flow through the tube has been seeded by an aerosol. And everything here was just isothermal. And it's then nice to see what actually happens in the mixing layer if you change the Well number and Reynolds number, play around with the parameters of the sweep velocity, which was here limited because it was by that time a Galvo scan mirror, very simple and cheap device, but limited in the scan rate just to see what you can do with that. And the scan angle was here chosen such that with a certain distance, we have had not only 50 by 50 millimeters in plane field of view, but the scan region as well was rather large with 50 millimeters. Of course, you have then to use an imaging system stop down such that in all planes you have still a reasonable resolution, meaning your depth of field must be adapted to that. And that's why that is rather large with Mie scattering, which is rather intense, that was still doable. It's a very simple setup using a high-speed laser, forming a sheet, sending it to the scan mirror here, which is a small device, bringing the laser in a certain angle range towards this cylindrical lens, which is then focusing in the laser light into sheets, which are schematically shown over here, and then it's scanned forth and back. And the CMOS camera shown over here, as I said, is equipped with a lens system that provides sufficient depth of field in for all cases. You see here a single image with quite some structures from the Mie scattering, and the idea is now not to follow all these small details because you have a discretization, of course, in the out-of-plane direction, which is not as good as the in-plane direction, and that's why it is here filtered to remove all these small structures. Then this low-pass filtered image has been corrected for the laser beam profile to avoid that you have, when you now take a threshold to track these mixing lines over here, that you can use a threshold which is applicable over the whole height of that image. So after beam profile correction, you get something like that, and with a simple threshold algorithm, you can distinguish now the area of the jet from the co-flowing area which has not been seeded by any particles. And so let me start that movie. It takes long until it comes directly. So what has been done here, the mirror has been scanned at low speed. 250 Hertz means one round tip, one direction and back. That means for one sweep, only half a period. That means takes place in 500 Hertz, which corresponds to 2 milliseconds. Then the laser has been operated with 30 kilohertz, such that you achieved 60 planes during one sweep. And you have to make sure that the sweep is fast enough against the timescales you want to resolve. And so let's call that an instant. Of course, that is true only because it's so slow for low Reynolds numbers, which are here in the order of 1,000 only of the jet and the annulus with 800. Because there was some shear, you see as well these structures very nicely that are formed. That is here without any swirl. And of course, it breaks up into finer structures if you have higher swirl. And so that is shown here. This is now one instant, yeah? That means within 2 milliseconds taken. You just show that by tech plot from different directions, and then you get a time resolved. Or you do it here with higher swirl. Then you have richer structures, smaller structures that appear. Here eventually you have the limit where you have only 50 millimeters captured. So the mixing already at this height was slightly larger as the direction in out of plane. And then you see actually the same thing, quite interesting to follow that now as well in time. So nothing which is unexpected, but very limited in terms with this resolution, 60 planes, to rather low Reynolds numbers. If you now crank up the Reynolds number and go for the maximum rate this scanning mirror allowed, then you have here it was a factor of 10. One sweep take now is 0.2 milliseconds, which is of course not bad, but for high Reynolds numbers still not sufficient. But you lose now the out-of-plane resolution, because you now have here only, now you have here 60 kilohertz, the previous one was 30, and that means we end up with only 12 planes instead of 60 as before. So still, you would say it's nice to see, it's a nice demonstration, that's clear, nothing really complicated about it, but the spatial resolution is too low because the repetition rate is of these devices, of the scanner, too low. And so you need a better equipment. Of course, you do not like to rely only on the reconstruction algorithm, because if there are small structures in between these planes, which you can clearly see here now, yeah, it's very badly discretized. Of course, you can fill them up somehow, but that's no information. That's just a best guess. So what is not resolved cannot be reconstructed without a priori knowledge, and that is nothing we have. We just want to measure it without any presumptions. So we have the need for higher scanning rates. How to do that? So a couple, maybe 2-3 years ago, I looked for a capable student coming up with ideas how to do that better. And the simple idea is to use, instead of a Galvo scanner going back and forth, which always is limited because of the inertia of mass, to use a Polygon. A Polygon, which is now operated up to 40,000 RPM, and with, in this case, 16 facets. And then you use a high-speed laser, and while the polygon is moving, the angle between this facet and the incoming beam is changing, and thereby you can see how the scanning is obtained. Afterwards, you have, of course, again, collection optics that is then parallelizing that beam, and later on you focus it into your region of interest. And the benefit of this device, still being mechanic, is that you can increase now the scanning rate up to 10 kilohertz. That was something of the limit we could achieve. And already this is getting a bit frightening, because now you have a device in your lab, a polygon of this size, turning very fastly, and that needs to be controlled to be, ideally free of any jitter. So this is a control problem, because every time you have your swept planes, you would like to have them at the next sweep, ideally at the identical position again. And that is, of course, difficult. What is the limitation? The spatial resolution still is given by the repetition rate of the laser. We can do better than 60 kilohertz, depends on your budget. You can go up to 200 kilohertz these days, but still the more energy you put on that facet, there as well may be occurring some degradation. So for the visible, that is less of a problem compared to the UV. And then the scan rate determines, of course, the temporal resolution. How long does it take to bring the light sheet from this edge to this edge? And that is, as I said, this time should be shorter, of course, than the time scales you want to resolve. And that means the challenge is here to increase the revolution speed or the number of facets. But there is as well something like a limitation. The more facets you have, the more of these edges you have. And given that you have a certain size of your beam, then you have here a lower duty cycle. And that was as well a design criteria from our side, saying that you would not like to have a duty cycle lower than 60%. And you cannot focus, of course, your beam at that facet, you will blow it away. So to develop that device and check whether the control strategies that have been developed in this master thesis are okay, there was an experiment to look for the jitter. You have here the laser, which is then brought to that polygon, where you have here these parallel light sheets, which are then formed through a telescope that has been laid out by ZMAX into this jet flow that was then later on a jet flame. So you have a surrounding co-flow, which is at low speed, and then there is a small tube with chamfered edges that has been used very often in the previous times as well for looking for lifted flames or high-speed jet flames. And then is here one CMOS camera, which is synchronized to the pulses from that laser and looking on the top of these sheets. If this is the sheet, the camera was looking on top of that to see its out-of-plane position, to observe the out-of-plane position. And then we just compared statistically the spatial variation with a fixed polygon scanner, meaning at 0 kilohertz. You find here naturally occurring pointing instability. Each laser is characterized by its pointing instability, which then, of course, causes a certain jitter in the location where you perform your measurements. And if you take this occurrence here, then you find something like a 1 sigma deviation of roughly 5.7 micrometers. If you now operate the system at 5 kilohertz, then you find a jitter which is slightly larger, but only by 0.3 micrometers, to increasing that to 6 microns. That is not a big deal. That is a proof that the control of that mirror seemed to work properly. If you go for the difference between minimum and maximum positions, that increased from 38 to 40 microns. So that is a rather stable system, at least at 5 kilohertz. You can do now as well an experiment at 10 kilohertz, but then you see an increased jitter. And the problem is really for each scanning rate, you have to adapt the control parameters. That's one thing. And the other thing is if you operate the polygon now at higher speeds, then your friction losses shoot up non-linearly. And that means that the power on the motor is getting higher, and the jitter increased here to something like 20 microns without really optimizing these parameters. As well, it's not only the optimization of the parameters, this polygon should now as well either operate it in a vacuum or in helium atmosphere to reduce the losses. And that's quite an effort. Yeah, but in principle, I think as well here you could reduce it remarkably down from the 20 microns, maybe down to 15 or 10. So still, for some applications, that seems to be okay. When the light sheet is in the order of 200 microns or 150 micron, this is in the order of 10% jitter. Not perfect, but maybe acceptable. We haven't followed that up any further because of reasons that become clear later on. So first, I would like to show the limitations of that polygon scanning device, dependent on the scan frequency, which has been changed from 2/5 to 10 kilohertz, and with a laser repetition rate at 532, which was 50 kilohertz. And that has been then applied to a turbulent flame of a lifted flame, where we then did this volumetric reconstruction using scattering of Mie particles, yeah, that have been seeded to the flow. So the experimental setup is the same, but now we are using this camera, which is looking from the side and gets the planar images from these different planes, of course using a lens system that is adapted such that the depth of field is sufficient. Not a very spectacular flame. This was a lifted jet flame operated with a Reynolds exit number of 5,000, co-flowing air, which was operated at 1,600 Reynolds number, and then simply using the change of the seeding density once you enter the flame. In terms of oil droplets, of course, they are vanishing, they're burning, such that you have a very high contrast with having no seeding and no Mie scattering inside the flame or inside areas where it's hot, and outside you have Mie scattering. Using chemically inert particles, for example, this alumina oxide, then it would be just a density jump. So then everything has been directed on the region of interest, which is here a region corresponding to the liftoff height. Of course, you do have some variations, but that was with this Reynolds number always within this area where you have the light sheets. For each of the planes, you have to calibrate, of course, your camera, because using a calibration plate like that, for example, because depending on the location, you have different magnifications, and that needs to be accounted for. So this might be time consuming, but is then actually needed such that you don't have any distortion or aberration due to that fact that the magnification is different for these different locations. And then you receive images like that is now given for one plane, for one realization, a raw image showing the Mie scattering in areas where you still have unburned gases, and then areas appearing here as black where the particles has disappeared due to the combustion of these particles. That is not good enough to reconstruct, and so I included that, for example, how post-processing can be done. Of course, that is just one out of an infinity of possibilities. There is no the correct way. Image processing is something like a black art. You have to document it, but in the end, you have somehow to show that the processing leads to the results you want. So I show this as an example over here. First of all, the images have been normalized such that you have all over the place intensities between 0 and 1. Then it's low pass filtered, and you see then these gradients here that have been slightly distorted, but as well these noise structures over here, which are actually no flame front wherever they come from, are as well a bit smoothed. Then again, it's normalized, and you already see that you have here, by this procedure, these small areas over here have been removed. Because in the end, we want to have a threshold algorithm that follows only these areas where you think the flame front actually is. Then it's median filtered. Again, by that, using the right size of that, you're removing some of these holes in between without harming these large areas. Of course, by all these procedures, you're losing spatial resolution in these structures, but looking at them, what is here real, what is here noise, I can't tell you. So that is anyhow questionable if you would try to keep them. Again, it's low pass filtered. You remove even more of these filters, holes, and normalize it. And then based on these images over here that look much cleaner than the original one, you see here how then the gradient operation has been divided this image into areas where you have low gradient shown as black, and white lines are showing then these gradients. Yeah, and from that you use these extracted information, you overlay that to the raw images, and then following that things you can, either you're satisfied or not. In some areas it's not easy to tell what is the truth. Of course, here where you have had a good image quality with a big gradient already in the original image, it's okay. But here at the side, you find, of course, some areas where it's not so clear. But with that, you have at least an estimation with a certain spatial resolution, which is very difficult now to quantify, a reconstruction between burned and unburned. With that, you have that now in different planes. You do it with 2 kilohertz, meaning scan rate that you have more out of plane resolution compared to a higher scan rate, because for the fixed laser repetition rate you have a much coarser resolution. And then you get an idea where actually here, wait for until it come back, where the flame has been located with its leading edge. With its leading edge over here. Yeah, so in between, you see here is the cold jet. The outside is cold from the cold flow, and the reddish area is then actually where the flame is. And you see here that would be the leading edge, some reconstruction artifacts, I would say, that it cannot be true. So those are you see the limitations of the reconstruction. These things are not autoignition or something like that. Yeah, this is artifacts. So you get some idea what is going on. Now you have to somehow evaluate that. And this is done here in 2 ways. First of all, it's an in-plane correlation. So the question is, how well correlates one image with itself at the same location after one sweep. So you take the image at this location, and then the light sheet is scanned and it comes back, and in the next cycle you take the same location and correlate the measured image with itself. And by that you can test the temporal resolution. If you would have an extremely fast sweep, then the flow would not have changed remarkably. Given with the resolution you have, you would have a very high correlation. If the flow has changed in between a lot, your sheet comes back and the flow has changed and the correlation is low. And so, of course, you expect the higher the scan rate, shown green for 10 kilohertz, the better the correlation. And the correlation is here shown for certain positions. And you see, this is out of plane, you see that the correlation is in the order of, let's say, 0.7. And for 2 kilohertz, you see it is reduced to something in 0.5. Okay, so that's not unexpected. Of course, it shows you that even the 10 kilohertz for this low Reynolds number, Reynolds 5000, might not be sufficient. Yeah? Ideally, it's now up to you what you want, but maybe ideally you would like to have it at, I don't know, 0.95 or something like that. So clearly it's not fully resolved. You can do now another check, the out-of-plane correlation. And here you ask the question, how well correlates one image with the neighboring one? So within one cycle, within one sweep, you go from one to the other plane and look for the correlation, the cross-correlation between the intensity distributions of these adjacent planes. This is a measure how well the spatial discretization is in scan direction. Yeah, when these, let's say, these fingers are now the intensity structures. If they're identical at the other plane, then you have a very high resolution, meaning that the correlation value would be 1. But if not, if the resolution out of plane is not good enough, then you're or not perfect, then you have a correlation which is lower than 1. And as expected, at 2 kilohertz, you have a higher discretization, and that is here the driving factor, such that these higher discretization gives higher correlation values. With 10 kilohertz, of course, it's then reduced down to something like here, down to 0.1, which is not very good. That is clearly an indication that the out-of-plane resolution is rather coarse. Yes, please, your question.
When you have a turbulent flame, say something that's actually distorted by a turbulent eddy, shouldn't you expect in that spatial correlation that it actually goes down to 0 if you're fast enough?
So the question is, in a turbulent flame, it should go down to 0 if it's not fast enough?
No, if it's fast enough, then because of the way that the eddy distorts the flame.
Yeah, but in the spatial direction, if the resolution is very high, then as long as you stay within the eddies themselves, you would still see a high correlation. Of course, this depending on the in-plane resolution you have. Let's say because of the filtering, you're not looking for the Kolmogorov eddies. You're looking for, let's say, medium-sized and large eddies. And as long as you're, of course, the correlation is to be expected to reduce clearly. Yeah, that's true. That's maybe that is maybe the error I made saying it should be 1. That's maybe your point you have. Of course, it will reduce when you have even a small step size. That's correct. It will not be 1. That's a good point. I was incorrect. Okay. So, in general, you can say if you have a high scan rate with a rather good temporal resolution, that comes along with a bad out-of-plane discretization. And so still here, that is only a beginning. In principle, you need faster lasers and still higher scan rates. So what about smoothing? Is that anything changing? If you now release your spatial resolution, and that has been done here, again, for these 3 examples. And as you see, a lot of the structures that still have been seen at the 2 kilohertz sweep have been now removed. Everything looks now a bit maybe nicer. Still, you can of course follow this leading edge that is with a slow motion showing how the flame is now competing against the approaching flow. And if you now do the same analysis, the in-plane and the out-of-plane correlation, then you find, of course, for the filtered data, correlations more on that side that you would like to have, but of course on the expense of the in-plane resolution. And it's now, of course, questionable whether you would like to do that. You just have to be aware of the fact that the small structures have now been gone completely. Yeah. Still, the large structures like lift-off height that might be still visible, and still you could identify whether that flame is stabilized by auto-ignition kernels, for example, or not. But learning about the small-scale structures, the wrinkling turbulence chemistry interaction, that is not feasible anymore with this kind of smoothing. However, here you see now a reconstruction of one single shot, and for the flame for the same flame, we have obtained or performed as well chemiluminescence measurements. I will not go into them. That have been tomographically reconstructed. Instead, later on, I'll show you some ideas about LIF, more recent. And we did that here then and overlaid that for a statistical mean. As you see here in blue, that we then, with the chemiluminescence image from experiment that has been conducted, I think 10 months later, you find rather similar results from that methodology as well. So it seems to be matching, but as I said, only good for really large structures. So if I sum up these performances, the jitter in low speed scanning was better than 8 microns. It was only slightly increased compared to the natural jitter, just a second. That was operated in air. If you operate at higher scan rates, we needed to reduce the friction, and that was a helium atmosphere where we still had 20 microns jitter, but without any optimized parameters for the control. So we are much faster than Galvo scanners that are commercially available. And you have then, depending on the question you ask, to find a compromise between your temporal and spatial resolution. Overall, you can say the higher the pulse rate of your laser, the better the reconstruction would be. Very important, data post-processing is a crucial step. And my advice is that you perform a proper documentation such that it is clear where your limitations come from, for example, in terms of spatial resolution. Okay, your question, please.
Is there a reason why the flame slices are smooth and not interpolated?
Of course, you can interpolate a filter. A filter, okay, the question is, why is it smoothed and not interpolated? If you use a filter in post-processing volumetrically, in the end, it is, of course, the effect would be very similar, I would say. The effect would be similar. It is computational, I guess it takes more time. If you know, for each of these planes, maybe make an interpolation based on, I don't know, polynomial of second order, third order, or whatever. That is computational more expensive. So in this post-processing based on MATLAB as we that do, this is a filter operation that is rather fast. Okay. Now, how to achieve higher scan rates? And I apologize, that is now 1 or 2 slides in addition to those you have in printed version. I just added them because simply I forgot that as I prepared the lecture, and you find now as well a paper on that just has been published a couple of days ago from my PhD student Tao Li as first author, which is in Applied Physics B 2017. So this mechanical scanner, of course, that's a challenge and that's quite cool as a project. You learn a lot about mechanics, about control circuits and so on. But in the end, it's not so practical. Yeah? You have a device that can be dangerous if something goes wrong. You have a housing to protect yourself for high scan rates. You either need a vacuum or helium atmosphere. So nothing of that is really what you like to have close to already a very complex system of combustion. That's why having a device without any mechanical parts is much better. And so why not using an acousto-optic deflector? This is a well-known technology that is used in different environments for a long time, and you can use it as well as a scanner. So the idea is that you do have here a crystal that is attached to a piezo transducer that creates an acoustic wave with a certain frequency or with a certain wavelength. And then this wave travels through this crystal and is absorbed up there, like in a system like a Bragg cell for laser Doppler velocimetry. And then you can deduce a relation that gives you the Bragg angle of constructive scattering given by that wavelength of these acoustic wave and the wavelength of your laser beam. And then in these directions, if you now direct your laser like that, then you find for a certain wavelength here a Bragg reflection first order maybe in that direction with a relatively high efficiency. Yeah? If you then look into this direction and form a light sheet, then this would be one plane. Now for the next laser shot, before that comes, so the first laser shot is over, you have the beam going into this specific direction. Now the laser shot is over, you change by your driver over here the acoustic frequency, you change thereby the wavelength, and then at the next instant, for the next instant I mean the next laser shot, the whole crystal here is filled with an acoustic wave with, of course, the one wavelength, not like shown over here, this is just for demonstration, Let's assume that you now, for the second shot, have this acoustic wave with that wavelength all over the crystal, and then you find the Bragg condition fulfilled into a different angle. And that means the incoming laser beam is now leaving the crystal, first order reflection here, in a different direction. And thereby you can scan. And the scan frequency is limited only by the fact how long it takes that an acoustic wave travels from here to here, because that is the minimum time you need to switch from one frequency to the other, because you would not like to have different wavelengths, different acoustic wavelengths inside the crystal when the laser shot comes. Then you simply create something which is like a diverging beam, I guess. And that works relatively reliable, and it's a very simple and small device. And we have used that, is there an example? No. We have used that recently in looking into engines, where we have performed multiple sheet PIV. Okay? Instead of having tomographic PIV limited in the depth, 4 to 8 millimeters, in engines, typically you're interested as well in larger distances, and then taking one PIV vector map at one location, and then within the same cycle, a crank angle or 1.5 crank angle later in a different location. And that is just simply one optical component in addition. So that's, I think, a very, very charming concept. And that works very nicely for visible light, and currently we test that for UV. Okay. Any questions about that? Then let's have a look into the other concept where you not use scanning, but use multiple planes. In that case, that is a dual plane approach that has been developed in collaboration with Isaac Box and Wolfgang Meyer from the DLR in Stuttgart. And so I will show you the concept in an atmospheric pressure system where we looked at a freely propagating flame, and then as well the use of the same concept in an IC engine where we looked to the early flame propagation, where our goal was to measure the turbulent flame speed as a very, very important quantity in modeling of premixed flames. So the turbulent flame speed given by ST in direction normal of the instantaneous flame front is a key parameter. It is important to understand the rate of fuel consumption. Of course, it's 3D, and you have no chance to achieve that somehow with a 2D technique. So what you need is a multi-parameter technique, as you will see in a second, which is temporally resolved and volumetric, or quasi-volumetric. So regarding the background for premixed flames, if you have an overall flame propagation shown by this red arrow, for example, a flame element that is transported in a certain time step from here to here, then you can decompose that into a part due to the convection and into the part which is here the turbulent flame speed, or very often as well called displacement speed, which is normal to the instantaneous surface of the flame front. And of course, the convection goes in one direction, which is completely uncorrelated to the location or to the orientation of that surface. And so if you measure somehow the overall flame propagation speed and measure simultaneously the convection speed and measure the orientation of the surface of your flame, then you have here a chance to estimate that turbulent flame speed or displacement speed. And so this is visualized over here in a 2D schematic. Of course, everything now is 3D. There come some illustrations later on about that. So you measure the flame front, for example, by OH-LIF in a sheet here. And with a certain resolution, you receive here the apparent flame front. Maybe you do not resolve all the wrinkling. Yeah, this is just to make clear that these techniques combined with the intensifier and so on are not capable to look for the small structures. And then you do the same, but temporally slightly displaced, maybe 50 microseconds later, depends on your system. And then we look at this flame element over here, which is transported by convection, and it's then due to the reaction diffusion in a premixed flame, which is then perpendicular to that instantaneous flame front position, is then transported to the final location of this flame element. And for that you need the orientation of this flame normal. So if you rearrange that, you then are able to deduce this ST if you have an estimation of the surface orientation, an estimation of the flame propagation speed and the convection speed, which you need in all three, where you need all three velocity components. Coming back to the orientation, you need a 3D flame front tracking. You cannot do it 2D. You need it 3D. And then you can extract the ST. Okay. So how is that done? The idea is rather simple. You perform a measurement with two OH sheets which are parallel to each other. Let's say this is the plane number 1 here at 0.5 at this height, and the other one quasi-simultaneously measured is that one with Z minus 0.5. This is below. At these two planes at time 0, at the first laser shot, you achieve this flame front in the upper sheet and the blue one in the lower sheet. And then with some reconstruction and of course smoothing, you then can estimate the flame front by a simple interpolation between these two measured flame fronts, which here appear of course as lines in a 2D projection. It would be desirable to have more than these two light sheets, maybe 3 or 5, but that's simply as well a question of not only money, it's not easy then bring them together. And then you repeat the experiment maybe 50 microseconds later, such that you then have the flame transported to this dashed line in the upper plane and to the dashed blue line in the lower plane. With that, you can estimate now, due to this linear interpolation between these two locations of the flame front, you can estimate the flame front location in the plane between these two OH planes, the plane which spans here at Z0, yeah, which is sandwiched by these two OH planes. That is this location over here. Then you know the velocity in this plane if you perform at this plane 0 stereo PRV. Yeah? Now we have a OH plane, a stereo PRV plane, and the other OH plane. Such that you can, with this information on the velocity, with all three components, you know now where the flame front would have been transported to if you would have only convection. Yeah? Only this part. Yeah? The flame, of course, consists not only of the convection, transport by convection, but as well due to diffusion and reaction, it has as well this flame speed itself. And so what you do now is you have here the estimated location where the flame front would have been transported to. Of course, because of the out of plane from the stereo PIV plane, it's not a line which is in the Z0 plane. It has been, of course, kinks and goes out. And now you compare with the information of the orientation of that flame sheet. You go to that line, you assume the orientation from that instant, and you draw perpendicular to that surface. You draw now arrows until you hit the surface that has been reconstructed, shown here already for T0 plus delta T LIF. You have a distance now between this black line and the surface, which is not easily to be seen here in this projection, that hits then finally the surface. And with that, I magnify that now here. You can determine this term NST. You can do it as well backwards. In principle, you would find very, very similar results if you would do this procedure starting from the later time and go to earlier times. And that is something which is was demonstrated first in an experiment where we have used here a large tube. that was something like 2.5 meters long, 160 millimeters in diameter, that was operated with premixed methane air that was constantly flowing. And then there was here an ignition, and then a flame kernel developed. Why so long? We wanted to have, by that time, fully developed pipe flow turbulence, and we wanted to have a large diameter such that we had a certain distance in space where we have not yet any air entrainment from the surrounding co-flow, which was operated at similar flow velocities. And then you see here a high-speed CL camera that looks for the overall flame propagation. Then you see as well here the two stereo PIV cameras that were using that plane for measuring the 3 velocity components. And then you see here 2 OH PLIF cameras equipped with image intensifiers that were looking at these 2 planes. Slightly displaced to each other in time, so only quasi-simultaneously, and the distance between these planes as well has been varied. In the end, for that experiment, I think it was 0.5 millimeter or 1 millimeter, I'm not sure anymore. Here, this was a parameter that has been as well varied. And so, magnifying that view, it was a rather small area with a high magnification corresponding to something like this European sand, where you see here where the light sheets came through. This was again UV sandwiching the green for the PIV with the cameras looking at this location. And here the flow has been spark ignited. So Reynolds number 10,000, equivalence ratio 1 for this case, and what is not as well important here, where is it? The Kolmogorov scales have been in an order where we think we can fully resolve that. Now you see here how the flame is propagating. This is chemoluminescence. Here you see the Mies scattering, and now this red angle says when the data has been taken. Now it was aerosol seeding, as you see here in that case, to demonstrate that. So the particles are vanishing once the flame goes through. So just to show you in slow motion what the experiment actually is doing. Then from these 2 OH planes, plane number 1 and here plane number 2, you see here the interpolated flame surface. The flame front shown here in blue at the intermediate plane where you have had the stereo PIV, as well with the, I think this is the flame normal direction. So with having that now temporally resolved, here that was with a high-speed laser such that we could get sequences, you can find now what the flame front actually is doing. Yeah, it's moving in space and time. Okay. And now, using that reconstruction I have explained, we can now, for certain realizations, look along that line for this quantity displacement speed. And of course, that is varying along that line. You see here color-coded the magnitudes from -1 to 2 meters per second. And here to the right-hand side, you see the corresponding histogram showing the number of occurrence for a certain displacement speed. And as expected, it's a turbulent system that has a wide spread, as well to values which are far above the laminar flame speed, which is around, I don't know, 0.38 meters per second for equivalence ratio 1. But as well, you find negative displacement speeds. And that's interesting to see. And that happens quite often. So if you now come up with a histogram from a lot of these shots and realizations and using only statistically independent data, you find a histogram that looks like that, where you have the maximum velocities here somewhere maybe 2.5, 3 meters per second, which are up to 8 times the laminar flame speed. And you find as well here these negative parts. And interestingly, you find as well the same results from DNS, from articles shown over here 20 years ago, 10 years ago, where the authors as well observed this negative displacement speeds. And that is linked to, in the end, changes in the flame structure that are caused by the convection caused by eddies interacting with these flame, which as well include thermodiffusive effects, and all of them are not accounted for in at least turbulent combustion models. So that's interesting. So when I go to exemplify that for the IC engine, I will point towards a certain aspect that I have not yet discussed. Maybe I should do it briefly and explain it again after the break. You have seen that we have taken the convection velocity at the estimated position of the flame front. Maybe I go back. Which one is maybe good? Here is the estimated position of the flame front with the flame normal. But as I'll show after the break, you have to take the convection velocity slightly up front of these flame front, upstream, no, sorry, this is downstream of the flame front. Why? Because if you would take it even with solid seeding particles at the flame front, you would have as well already density effects. And this definition I've shown is valid only for the fluid with the density of the unburned. And that means you have to take it slightly half a millimeter or so displaced from that flame front, which as well has a certain influence on that. Yeah? And that needs to as well accounted for, such that the interpretation of these histogram is maybe not that easy and straightforward. So negative flame speed does not mean negative consumption rate. Yeah? You're not producing fuel out of water and CO2. I think that's clear. Yeah? That would be great. It is as well dependent on where you have your isoline and measure that. Yeah? This is dependent on that as well. And this is given here, as I said, by the velocity taken at a certain distance from that, as well as where you track your flame front, which in our case was the maximum gradient of the OH. So if you would do that in a different isoline that can be easily done in DNS, not so easy in experiments, you would find a changed histogram. Okay. With that, I'm happy to take any questions. It's not the case. Then we have a break and continue with the discussion of this methodology in the IC engine in 10:05. Thank you.